Hello again. This is Mrs. Price, and it's time to do section 6.5, which is on the fundamental theorem of algebra. We're going to start with a little review warm-up kind of a thing. So our little warm-up here says, describe the solutions of each of the following and explain how you know. So how do we know how many and what types of solutions a quadratic equation has? Let's see if you remember, there is a word that we learned in a previous chapter called the discriminant, which is b squared minus 4ac. So for our first problem, a is 1, b is 1, c is 1. So we have 1 minus 4 times 1 times 1, or negative 3. When our discriminant is negative, remember that this is the stuff that's under the root in the quadratic formula, right? Negative b plus or minus square root b squared minus 4ac all over 2a. This right here is under a root, which means that if our discriminant is negative, that means that we're not going to have any real roots. We're going to actually have two imaginary or complex conjugate roots. For the second one, our b is 2, our a is 1, and our c is 1. So we have 4 minus 4, or 0. When you have a 0 under this root, this plus or minus just means you're adding and subtracting nothing. So your only root is negative b over 2a. So because of that, you end up having just one repeated real root. And so we could also say that this is a single root with a multiplicity of 2. Finally, this third one, our b is 3, a is 1, c is 1. So we have a discriminant of 9 minus 4, which is positive. When you have a positive discriminant, it means you're going to have two real roots. All right, we don't have to actually find them. We just wanted to describe them. So a little review of discriminant. Moving forward. All right, so we're going to do a little review here. Consider the following polynomial function, 3x cubed minus 19x squared plus 13x plus 35. First thing we're going to do, just to review what we learned yesterday, is we're going to list the possible rational roots for this polynomial. So when we do this, we do the factors of the constant over the factors of the leading coefficient. So the factors of 35 are 1 and 30. Let's just go 1, 5, 7, and 35. Factors of 3 are 1 and 3. So we have to take all of these and divide them by both of these. I'm going to start with 1. So our possible rational roots are, so I have 1 over 1, 1 over 3, 5 over 1, 5 over 3, 7 over 1, 7 over 3, 35 over 1, and 35 over 3. All right, except there's a little thing I got to make sure I put with every term, which, I'm cleaning up these numbers here, is plus or minus, plus or minus, plus or minus, plus or minus. And we write this for every single one. And there are our possible rational roots. So factors of the constant divided by the factors of the leading coefficient. All right, part B, graph, because boy, I do not want to test, 10, 20 different rational roots. So we're going to graph this and see if we can find any x-intercepts that are integers. All right, so I have it graphed right here. And if we look, well, that guy's rational, so that's not an integer, this one right here. I think I already know what it is, but let's go ahead and just look at that one. We have one at 5 and one at negative 1. So we have two integer roots, one at negative 1 and one at 5. So our x-intercepts x equals -1 and x equals 5. There's another one that's rational that we'll have to find either by factoring or by synthetic division. All right, so I'm going to go ahead and synthetically divide out the -1. So I'm going to synthetically divide this -1 out first. So I'm going to write my coefficients going across. 13, 35. I think I'm just going to check. No, I didn't. I thought I gave myself an additional page. I can always add a page though. Bring down the 3. 3 times -1 is -3. Remember, multiply up, add down. Multiply up, that's 22. Add down, multiply up. Oh my goodness, I'm having trouble with my stylus. Add down. Remember, this last number is your remainder. As long as it's 0, it proves that this is an actual root of the function. So what is the function that's left? The function that's left, remember these are coefficients, you reduce the power by 1, so we'd have 3x squared minus 22x plus 35. Now, we could divide out the 5 and get down to the final factor, or we could try to factor this. Either way, it really is fine either way. Well, I don't know. It might be easier to divide out. We could factor, but we know that it's going to be a little bit complicated because there's a leading coefficient. Let's divide out just because I think that's the easiest route to take. So if I divide out my 5, bring down the 3, 15, -7, -35, 0. That's my remainder. Here's my final factor. So first, to relist the function f of x as a product of factors, well, we have our x plus 1, because our root -1. Oh my goodness. We have our x minus 5, because of our root of 5. And then this last guy here is 3x minus 7. Because we started with a squared, we reduced the degree by 1, so we're left with 3x minus 7. So this is our factored form of our polynomial, and our roots are at x equals -1, 5. And if we set this last factor equal to 0, we get 7/3. And there's our 3 roots. So a little squishy, but we did it. All right. So the fundamental theorem of algebra is actually pretty simple. What it really says is the number of complex roots that a polynomial has is the same as the degree of the polynomial. So if a polynomial has degree n, then it has n complex roots. So if a polynomial has degree 5, it has 5 roots. So notice that complex doesn't mean imaginary. Complex can be real, complex can be imaginary. It'd be a combination of the two. So if a polynomial has any roots with an imaginary component, remember there have to be an even number to account for the conjugates, right? So if I have one imaginary root, I must have another imaginary root. There's always got to be an even number of imaginary roots. However, you can have as many real roots as you want. So you can have an odd number of roots, but if you have imaginaries, there need to be an even number. All right, so we're going to do one big example and call it a day. It's a short lesson today. You're welcome. So for this example, with this big giant 5th degree polynomial, 5th degree means that we know we're going to have 5 complex roots. So we're going to see if we can find those 5 complex roots. So we're going to start by listing the possible rational zeros. So our factors of 24 factors into 1, 2, 3, 4, 6, 8, 12, and 24. Oh my goodness, there's going to be a lot of possible rational roots. Just 1 and 3 for the leading coefficient. So our possible rational roots would be 1 over 1, 1 over 3, 2 over 1, 2 over 3, 3 over 1, Now 3 over 3 is just 1, so we don't have to write it again. 4 over 1, 4 over 3, 6 over 1. 6 over 3 is 2, which we've already got, so we don't have to write it again. 8 over 1, 8 over 3, 12 over 1. 12 over 3 is 4, which we already have. 24 over 1. And then 24 over 3 is 8, which we already have. So here's all of our possible rational roots, except we got to put our plus or minus in front of every single one. And there we go. All right, so part A, possible rational zeros. My goodness, that's a lot of them, but that's okay. Because now for part B, we're going to look at the graph, and we're going to see if we can narrow this list down. So I'm going to switch over to Desmos, turn off my first graph, turn on this graph, and here's what we've got. So it looks like we have a 0 at -1, a 0 at 3, and then something that's in between 0 and -1. So -1, 3, and then a number in between 0 and -1. All right, so we've got something, so we have an x equals -1, an x equals 3, and then something between 0 and -1. All right, next step. So we're going to synthetically divide out those integers. So I have a -1, and I'm going to rewrite my coefficients. -1, -22, -52, -24. Leave a little space, draw a line, bring down the 3, multiply and add. Multiply, add, multiply, add, multiply, add, multiply. Let's see. Yep, that is 24, except it's negative. Positive 24, 0. Now, what's nice about synthetic division is if you have to synthetically divide out multiple numbers, you don't have to rewrite the whole problem. You can just keep going. So our other 0 was at 3. So I'm just going to put the 3 there, divide it into these, and see what's left. So bring down the 3, multiply, add, multiply, add, multiply, add, multiply, add, da, 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 da. And so let's see what we've got now. So I'm going to rewrite my function just as a product of factors so you understand what's going on. So from the root of -1, I get x plus 1. From the root of 3, I get x minus 3. All right, I had a 5th degree. I started with a 5th degree. So this line would be a 4th degree, which means this line would be a 3rd degree because I've divided out an x and I've divided out another x. So what I'm left with is 3x cubed plus 2x squared plus 12x plus 8. All right, and let's see if I can capture this on the next screen. So I have f of x equals x plus 1 times x minus 3 times 3x cubed plus 2x squared plus 12x plus 8. Now, this can actually easily be factored by grouping, but we need to practice long division. So what we're going to do now is use long division to divide out any rational roots. So if we take a look, we have a root somewhere between 0 and -1. So let's go back to our screen where we listed the possible rational roots, and let's see if we can find the ones that are between 0 and -1. We have a -1/3 or a -2/3. We don't know which one it is. I'm going to check the graph and see if I can kind of make a judgment call. So it looks like it's more than halfway, so I'm going to try the -2/3 just to save us some time. So we're going to divide out this guy by x minus 2/3. Now, just so you know, when you're dividing out x minus 2/3, it actually is sometimes easier if you consider just dividing by 3x minus 2. You end up with the same, how do I say this? The same result, just a little bit cleaner. So I'm going to, Okay, so I was about to start dividing, and then I realized that my root was actually negative, and this had to be a plus. So I'm fixing that now, and I'm going to divide by x plus 2/3 into 3x cubed plus 2x squared, 12x plus 8. All right, so remember, you look at your first terms. What do I have to multiply x by to get 3x cubed? Would be 3x squared. And then I distribute this down, so I get 3x cubed plus 3x squared times 2/3 is 2x squared. So here's the kicker. Be careful, because remember, you're subtracting down. So when we subtract down, we actually end up with 0. So now we just bring down these two remaining terms. Whoops, that's an x. And we ask ourselves, what do I have to multiply x by to get 12? And that would be 12. So 12x, so I multiply down, I get 12x plus, and what is 2/3 of 12? It's 8. So if I subtract this down, I still have a remainder of 0, and there's my quotient. So my new f of x right now is x plus 1 times x minus 3 times x plus 2/3, we'll talk about that in a little bit, times 3x squared plus 12. All right, so there's my new factored form of my polynomial, and now we got to deal with this 3x squared plus 12. All right, so I'm going to rewrite it again. So I have x plus 1, x minus 3, x plus 2/3, and 3x squared plus 12. All right, now we've got to find these final two complex roots from 3x squared plus 12. We can just solve this simply by setting it equal to 0, subtract 12 from both sides, divide by 3, take the square root of both sides, make sure you put a plus or minus, and we end up with x equals plus or minus. Remember, this is root 4 times root negative 1, so our x equals plus or minus 2i. So did I ask a final question? I did. So we're going to list, I'm going to rewrite my polynomial on this next screen. So I have f of x in factored form would be x plus 1, x minus 3, x plus 2/3, x plus, was it 2i? Yep, 2i. X plus 2i and x minus 2i. So this is my new factored form. I'm kind of doing part G first. That's part G. So part F, when I list all the zeros, what do I get? My roots would be negative 1, 3, negative 2/3, negative 2i, and positive 2i. And that's what I get. Hey, does my answer follow the fundamental theorem of algebra? Well, let's see. I'm going to relist our roots. So we had for roots negative 1, 3, negative 2/3, negative 2i, positive 2i. Let's count. 1, 2, 3, 4, 5. This is a fifth degree polynomial. Yes, it checks off. And that's it. That's all for the lesson today. So hope this helped you kind of review what we've done so far, helps you understand the relationship between the number of complex roots and the degree of